While Galileo's telescope allowed us to take an outward voyage, another innovation, here in the Dutch town of Delft, would lead us on an inward journey of discovery. Over 3 centuries ago, Antony van Leeuwenhoek perfected the early microscope and used it to study droplets from the waterways of Holland. As students today make their own discoveries, imagine the moment when Van Leeuwenhoek peered through his more powerful instrument and discovered a living kingdom in a drop of water. This busy world of single-celled paramecia is only 1 millimeter across, 3 pounds of tin smaller than a meter. The microscope allows us to continue our journey into the realm of the very small. As we move into the cell nucleus, each new ring now reveals a world 10 times smaller in diameter than the last. Deep within the nucleus, we come upon truly remarkable constructions, long spiraling molecules of DNA. DNA holds the chemical codes for the reproduction of most organisms on the planet, whether they're paramecia, people, or petunias. Voyaging on, we see that molecules are made of even smaller parts called atoms. The tiny world of the carbon atom is very strange indeed. Its 6 electrons seem to swarm everywhere at once. Now our voyage takes us through a void that appears as vast as the space between the stars. Ahead lies the atomic nucleus, so fantastically small that if the whole atom were the size of this theater, its nucleus would be like a speck of dust. Yet the nucleus contains almost all of the atom's mass, packed into particles called protons and neutrons. And these, in turn, are made of still smaller, mysterious things called quarks. Exploring this, the inner frontier of the universe, physicists wonder if quarks might contain even tinier building blocks of matter. Scientists are investigating this mystery in an underground tunnel near Chicago, home of the giant Fermilab particle accelerator, designed to create conditions like those that existed just after the birth of our universe. Millions of protons and antiprotons race through these pipes in opposite directions, nearly at the speed of light in a kind of subatomic demolition derby. Now, our cosmic voyage enters another dimension, the dimension of time, where knowledge is much less certain. Studying traces of quarks from these collisions, physicists try to learn what our universe was like when it began after the explosion known as the Big Bang. One of them outlines the theory.
Welcome to Fermilab. Today, astronomers see the universe expanding. Imagine running the expansion backwards. Billions of years ago, everything must have been packed together at enormous density. It seems incredible, but we think that the matter making up everything we see in the universe today, everything, the buildings, trees, people, planets, stars out to the most distant galaxies, was once crammed together into a volume smaller than this. And then
space itself exploded in a burst of radiant energy. In those first dazzling moments, the newborn universe began to expand and cool. Quarks combined into protons and neutrons, which later attracted electrons to form atoms, and the vast fog lifted. For hundreds of millions of years, the force of gravity slowly drew matter together into a gigantic web, the architecture of the cosmos. Two billion years passed. Clouds of gas and dust condensed like giant water drops along the cosmic strands and formed galaxies. Where the great ridges of matter crossed, galaxies came together in clusters. Some galaxies evolved into gigantic disks and spirals of stars, gas, and dust. Neighboring galaxies, trapped by their mutual gravity, draw together in a fantastic collision. In real time, it would last 1 billion years. The force of gravity strips long tails of gas and stars from the huge new galaxy. And yet stars almost never collide. So vast are the distances between them. Perhaps 10 billion years pass, and we encounter our own galaxy, the Milky Way. In it, stars have formed, and some have died. Stars are nuclear furnaces. They shine until they use up their fuel. Massive stars end explosively. These exploding stars, or supernovas, send out the elements of life. The oxygen we breathe, the carbon in our muscles, the iron in our blood. Now a cloud of cosmic gas, sprinkled with these elements, comes together in the grip of gravity. A new star, our sun, ignites. Around it, planets form. In their infancy, over 4 billion years ago, our Earth and Moon were bombarded constantly by cosmic dust, asteroids, and comets. With violent impacts, volcanic gases, acid rain, and potent ultraviolet radiation from the sun, the young Earth was a very hostile world. And yet, the basic ingredients of life were already here.